Hi everyone. We're going to go ahead and solve the first question from the homework involving escape energy and escape velocity. One of the things that is unclear with that very first question on page 235, number 1, is what's the mass that's trying to escape? If you don't have a mass that's trying to escape something, you can't solve anything. You need the mass that's actually escaping the planet. And so it does refer to the quick lab at the beginning of that chapter on that question. But it would be better if they would just put that 6 kilogram object into the question. So we have the question saying this with that information. Determine the escape energy and escape speed for a 6 kilogram object from an asteroid with a mass of this and a radius of this. And so the first thing we're recognizing is that the small mass is a 6 kilogram object. The large mass is the asteroid, much smaller than Earth's mass. If you compare that to 5.98 times 10 to the 24 kilograms for Earth's mass, it's about 600 times less massive. The radius of the asteroid, we're assuming it's a circular asteroid, or at least we're taking that as an approximation, is this. And so with that information, we're asked to figure out the escape energy and escape speed. Well, the other information we do know as well is the gravitational constant. And we also know that there's something happening with the escape energy compared to the gravitational potential energy. And if you think about it, the escape energy needs to overcome the gravitational potential energy. Right? We have to, gravitational potential energy is what's holding us into or onto that object. And we need to get just enough to get past that gravitational potential energy that's holding us there. And if you remember, gravitational potential energy from our lesson is equal to negative GMM over R, which means if the escape energy is going to overcome the gravitational potential energy, the escape energy that I need is equal to the negative of the gravitational potential energy. Another way to put that would be to say that the escape energy plus the gravitational potential energy is 0. That's going to get us just enough energy to escape. And so rearranging that, we get escape is negative gravitational potential energy. In other words, negative of negative GMM over R. So it's the positive of that. So the escape energy is just that. So you go 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times the mass of 1.00 times 10 to the 22 kilograms times a mass of the small object of 6 kilograms, dividing all of that by a radius of 1.00 times 10 to the 6 meters. Remember, they have to be in SI units, so you have to have them in kilograms and meters. And when you do that, you end up with a number of 4.00 times 10 to the 6, or just before I round this, I get this. That many joules. One more 0. So I get basically 4 million joules. To sig digs, we get 4.00 times 10 to the 6 joules. So that's the amount of escape energy that is needed to just get outside of the gravitational potential energy of that asteroid. The second part of the question should follow from our lesson, and that asked us for the escape speed. And if you remember, we said the escape speed comes from the fact, we're calling that VE, comes from the fact that the total energy must be bigger than or equal to 0. And in other words, the kinetic energy plus the gravitational potential energy must be bigger or equal to 0. And the minimum speed we need is when these are equal to 0. And so break that down in V squared over 2. This is the escape speed that's needed, plus, remember, this is negative GMM over R. And so greater than or equal to 0. For the min speed, we're going to make that now equal to 0. That's what the escape speed is. It's the min speed needed. So we can have a bigger speed than that, but that's the min that we need. And then we just go ahead and we set those numbers in. I don't think I need to break that down for you, but I will go through the steps here. of at least rearranging the equation, what we get is we add GMM over R to both sides. So we get GMM over R is a positive on the right side. And we get MVE squared over 2. The masses of the small objects cancel. I multiply both sides by 2. And I arrive at VE is the square root of 2 times G times M over R. And then subbing the same numbers in as I did before, that gives me an escape. Just going to put a little step that's showing that I would sub it there. And then VE is going to be 1.15 times 10 to the 3 meters per second. I think your textbook has 1.16 times 10 to the 3, but they just rounded it differently. That is the equivalent to 4,160 kilometers per hour. That's the speed you need to get off of an object that's 1/600th the mass of Earth. We're talking about incredible speeds to even get off of an asteroid, and it's quite a problem that rocket scientists get to deal with, and it's quite remarkable that we can deal with that and get things into orbit. Anyway, I hope that helps. Email me if you have any questions.